Okay, our final example we're going to do today is going to be example 6. And so we're going to change what the book says slightly. We're going to say f of x is x to the 5th minus 5x to the 4th. And what we're going to do here is we're going to find where is this function increasing and decreasing. We're going to find points of inflection. We're going to find where are we concave up and where are we concave down. And we're going to find our relative maxes and mins. So, slightly different. The book just wants, the book statement just is find the, try to use the second derivative test and determine your local max and min. But we want to kind of put everything together with this one. So, let's start out getting the first derivative, which is 5x to the 4th minus 20x cubed. I can factor this. I can factor out a 5x cubed. Let's see, 5x cubed. That'll leave me a x. So 5 comes out, 3 of the 4 x's come out, the other one's behind. We'll have minus 4, because 5 comes out of 20, leaves the 4. And the whole x cubed came out. So this is our first derivative. We need to know for our critical points, this is never undefined, so we just need to set this first derivative equal to 0, and that'll tell me x equals 0 and x equal 4. These are my critical points. I'm going to jump from this one down to the second derivative. I'm going to get it from the top form, because if you use it for the second form, you got to use the product rule, which is annoying. So we'll get the top form, which is 20x cubed. So 4 comes down, hits the 5, that's 20. Minus, let's see, 3 times 20 is 60. That'll be x squared. So the second derivative is, let's see, we factor 20x squared out. We'll have an x left over. 20 removed from 60 is a 3. And again, this is a cubic. It's not undefined anywhere. We're going to set it equal to 0. Set the second derivative equal to 0. And this will give us candidates to try for points of inflection. Okay, so we have, we're going to build up our table. We got basically, looks like 0s, 3s, and 4s. So give this a shot. So we'll say there's negative infinity up to 0. We'll have 0 itself. We'll have 0 up to 3. We'll have 3. We'll have 3 up to 4. And we'll have 4. And then we'll have 4 up to infinity. Okay, so let's take a look. We'll have f prime and f double prime. So we're going to want to build our chart with all the pluses and minuses. So x equals 0 is a 0 of the first derivative. And x equals 4 is a 0 of the first derivative. The second derivative is 0 at x equals 0. And it's 0 again at x equals 3. So what we need to do now is we need to just kind of grab a point from each region, and we need to see what are the derivatives, what signs are they, and then we'll need to see what's going on with 3 and 4. So 3 at the first derivative and 4 at the second derivative. So I'm going to look at negative infinity up to 0. I'll look at negative 1. So for -1, I'm going to be plugging into the first derivative. I'm going to be plugging into the x here and the x here when I go to check this. We'll have 5 times -1 cubed times -1 minus 4. So that'll be 5 is positive, -1 cubed. When you cube a negative, it stays negative. -1 minus 4 is negative. So positive, negative, negative. When you multiply them out, is positive. So f prime should start out as positive. We'll use 1 next because 1's between 0 and 3. So we'll get 5 times 1 cubed times 1 minus 4. So that'll be positive. 1 cubed is positive. 1 minus 4 is -3, so that's negative. So the end result from plugging in here and here in the first derivative is we're negative. I guess let's do 3 next to see if 3 is positive or negative. We'd have 5 times 3 cubed times 3 minus 4. That's positive. 3 cubed is positive. 3 minus 4 is negative. So we're negative there. 3 up to 4, we'll use 3.5. So we'll get 5 times 3.5 cubed times 3.5 minus 4. It's positive. Positive cubed is positive. 3.5 minus 4 is negative. So our end result's negative there. Then we'll use 5. 5 times 5 cubed times 5 minus 4. 5 is positive. 5 cubed is positive. 5 minus 4 is positive. So our end result is positive. So we get for f prime, we get our chart looking like this. So now for f double prime, I'm going to be plugging in to the x here and the x there. So we'll use kind of similar numbers. We'll start out with -1. So we'll say, all right, it's 20 times -1 squared times -1 minus 3. It's positive. Anything squared is positive. -1 minus 3 is negative. So we start out and we're negative. From 0 to 3, we'll take a look at 1. We'll have 20 times 1 squared times 1 minus 3. 20 is positive. 1 squared is positive. 1 minus 3 is negative. And so we get that we're negative overall there. From 3 up to 4, I guess we'll use 3.5. So 20 times 3.5 squared times 3.5 minus 3. 20 is positive, 3.5 squared is positive, 3.5 minus 3 is positive. They're all positive, so we are positive right there. If we try 4 itself, that's 20 times 4 squared times 4 minus 3. 20 is positive, 4 squared is positive, 4 minus 3 is 1, which is positive, so we're positive. Then finally, if we look at 5, I guess we'll do it over here. 20 times 5 squared times 5 minus 3. 20 is positive, 5 squared is positive, 5 minus 3 is also positive, so we're positive out in that region. Okay, so we got all of our plus minus stuff. Now we just need to go through and kind of write things up. I'm going to scoot all these test points I did. I'm going to kind of grab them and slide them over there to get some space to write our answer up in. So these were all the points I chose from the second derivative. We had like -1, 1, 3.5, 4, and 5. So here's our chart. Let's start out where f is increasing and decreasing. So f is increasing. Remember, it's where the first derivative is positive. On -infinity to 0 and on 4 to infinity as f prime of x is greater than 0 there. So we got where the function is increasing. Now, we need to look at regions where the function is decreasing. The function's decreasing from 0 to 3, at 3 itself, and 3 to 4. So we can actually combine all of this into one interval, 0 up to 4. So we'll say f is decreasing on 0 up to 4 as f prime of x is less than 0 there. So the first derivative was negative at that point, or that region, and that got our function decreasing. Okay, next let's do concavity. It's based on the second derivative. F is concave up on, let's see, second derivative starts being positive here at 3 to 4. It's still positive over 4, and it's positive beyond 4, so we can join all of this into one interval. So it's 3 on up to infinity. As f double prime of x is greater than 0 there. So second derivative is positive for that region, means the basic function, or the function that whose derivatives you were taking, is concave up. So we'll get f is concave down on, we're going to have to keep these split up because we're negative here. Second derivative is negative here on negative infinity to 0. And over here, it's negative from 0 to 3. But it's 0 at itself. It's not negative. Like in here, the missing value 4, we were positive to the left, positive to the right, and positive at 4 itself. So we're able to join them together. Here we're negative, and then we're 0, so we're not able to join them. So we'll say negative infinity up to 0. And then 0 to 3 as f double prime is less than 0 there. So that's where we're concave down, those two intervals. Okay, let's do points of inflection next. F double prime is 0 at 0 and again at 3. F double prime has no change in sign across 0, so it's 0 is not a point of inflection. But we do change concavity from negative to positive, so we change from concave down to concave up across 3. So 3 is our point of inflection. So f has a point of inflection at x equals 3. As x equals 3 is a critical, sorry, we don't care about critical points. As x equals 3, the second is 0. So f as x equals 3, the point of inflection at x equals 3 as, sorry, it's f double prime of x is 0 at x equals 3. And f double prime changes sign at x equals 3. So at x equals 3, we have a point of inflection there because our second derivative is 0 and our second derivative changes sign. So the concavity changed at 3, meaning it's a point of inflection. So last ones we need are the relative mins and relative maxes. Let's see if we can use the second derivative test on any of these. So we need to find a critical point of f of x. If the second derivative exists, then if the second derivative is positive, we have a local min, which we could say is a relative min. If the second derivative is negative, we have a relative max. If the second derivative is 0, it's inconclusive. So we have two critical points. We have a critical point here at 0, and we have a critical point out here at 4. The critical point at 0 has second derivative 0, which means the second derivative test is inconclusive. So we can't, that doesn't help us with what's going on at x equals 0, because the second derivative is 0. At x equals 4, the second derivative is positive. So at the critical point x equals 4, the second derivative is positive. So if the second derivative is positive, this says f of c is a local minimum. So what we'll say is f has a relative minimum at x equals 4 as x equals 4 is a critical point. So remember, by second derivative, we need a critical point, and then we need the second derivative is positive. And in our case, the second derivative is positive at 4. So we say, okay, as x equals 4 is a critical point, and f double prime of x is greater than 0. Now, the second derivative was inconclusive on this, but we could go back to the first derivative test and say we changed from positive, first derivative changed from positive to negative across the critical point 0, which means if you switch from positive to negative, you're going to create a local max, because this says tangent lines are slope positive, then it's slope 0, then it's slope negative, so it's going to create a local max. So we'll say f has, we'll use relative max. Could say local or relative, they mean the same thing, at x equals 0, as x equals 0 is a critical point, let's see, is it as a critical point or do we need it actually equaling 0 for the first derivative test? Let me flip back. That's all right, it's just a critical point. So we have a critical point, and f prime changes from, let's see, what is it, positive to negative? From positive to negative. Relative max at x equals 0, as x equals 0 has a critical point, and f prime changes from positive to negative. At x equals 0. Okay, so we are done. That's kind of putting it all together and doing everything. Recapping, first derivative positive tells you where the function's increasing. First derivative of a function negative tells you where it's decreasing. Second derivative positive tells you where you're concave up. Second derivative negative tells you where you're concave down. Point of inflection is if your second derivative is 0 and you have a change in sign. So we had 2 zeros, but only the change in sign occurred at 3. For relative max and min, we tried using the second derivative test here. We had a critical point with the second derivative positive. So if you have a critical point and second derivative positive, that corresponds to the a relative min by the second derivative test. For this one, the second derivative test was inconclusive because the second derivative test was 0. So we went back to the first derivative test and said I have a critical point with the change in sign from positive to negative. And if that happens, that's going to correspond to a relative max. So we will stop there, and that wraps up section 4.0.